what I want to do in this video is differentiate between the ideas of nucleophilicity, or how strong of a nucleophile something is, and basicity, And the difference is, on one level, kind of subtle, but it's actually a very big difference. And I'll show you why it's kind of confusing the first time you learn it. When we studied SN2 reactions, you have a nucleophile that has an extra electron right here. It has a negative charge. And maybe you have a methyl carbon. Let me draw it. Maybe you have a hydrogen coming out. You have a hydrogen behind it. You have a hydrogen up top. And then you have a leaving group. Right over there. And in an SN2 reaction, the nucleophile will give this electron to the carbon. The carbon has a partial positive charge. Let me draw that. Partial positive charge. The leaving group has a partial negative charge because it tends to be, or it will be, more electronegative. And so this electron is given to this carbon. Right when the carbon gets that, or simultaneously with it, this electronegative leaving group is able to completely take this electron away from the carbon. And then after you are done, it looks like this. We have our methyl carbon. So the hydrogen in the back, hydrogen in the front, hydrogen on top. The leaving group has left. It had this electron right there, but now it also took that magenta electron. So it now has a negative charge. And the nucleophile has given this electron right over here. And so now it is bonded to the carbon. Now, the whole reason I did this is because, OK, this is acting as a nucleophile. It loves nucleuses. It's giving away its extra electron. But it is also acting as a Lewis base. And as a bit of a refresher, a Lewis base, which is really the most general, or I guess it covers the most examples of what it means to be a base. A Lewis base means that you are an electron donor. And that's exactly what's happening here. This nucleophile is donating an electron to the carbon. So it's acting as a Lewis base. So the first time you see that, you're like, well, why did chemists even go through the pain of defining something like a nucleophile? Why don't they just call it a base? Why are there two different concepts of nucleophilicity and basicity? And the difference is that nucleophilicity is a kinetic concept. It is kinetic, which means how good is it at reacting? How fast is it reacting? How little extra energy does it need to react? So if something has good nucleophilicity, it is good at reacting. It doesn't tell you anything about how stable or unstable the reactants before and after are. It just tells you they're good at reacting with each other. Basicity is a thermodynamic concept. It's telling you how stable are the reactants or the products. So it tells you how badly something would like to react. Something would like to react. For example, we saw the situation of fluorine. Let's think about this. We saw the situation, actually I say fluoride. So fluoride looks like this. 7 valence electrons for fluorine. And then you have it swiped one extra electron away. You get fluoride. So fluoride is reasonably basic. It is more basic than iodide. So this is more basic than iodide. More basic than iodide. But in a protic solution, let me write it here, but less nucleophilic in protic solution. And a protic solution, once again, has hydrogen protons around. And the reason why this is fluoride, it wants to bond with let's say a carbon or something else, more badly, or maybe even a hydrogen proton, it wants to bond with it more badly than an iodide anion. And if it did, it actually will be a stronger bond than the iodide anion will form. That the fluoride anion is actually less stable in this form than the iodide is. If it were to be able to get a proton or give its electron away, it will be happier, but it's less nucleophilic. It's less good at reacting in a protic solution. And the whole reason it's less nucleophilic is because there are other things that are keeping from reacting. And we saw in the video on what makes a good nucleophile that in the case of fluoride, it's because it forms hydrogen. It's a very small atom. Actually, say a very small ion. And so it forms, so it's very closely held. The electron cloud it's very tight. And so what it allows is the hydrogens from the water to form a very tight shell, around. These all have partial positive charges. So they are attracted to the negative anion. And so they form a very tight shell, kind of protecting the fluoride anion, which makes it harder for it to react in a protic solution. So doesn't react as well. Doesn't react as well. If it was able to react, it actually will form a stronger bond than the iodide anion. So that's the big difference. And just so we see the difference in trends. So basicity, it does not matter what your actual solvent is. It is a thermodynamic property of the molecule or the atom or the anion. So if you looked at just pure basicity, the strongest base you see, and I'll just write hydroxide here, it's normally something like sodium hydroxide or potassium hydroxide. But when you dissolve it in, say, something like water, the sodium and the hydroxide separate, and it's really the hydroxide that is acting as a base, something that wants to donate electrons. So hydroxide is a much stronger base than fluoride, which is a stronger base than chloride, which is a stronger base than bromide, which is a stronger base than iodide. Now, if you were to look at nucleophilicity, just to see the difference, nucleophilicity, we saw that there actually matters what's the solvent, because the solvent will affect how good something is at reacting. So nucleophilicity, there's a difference between a protic solvent and an aprotic solvent. In a protic solvent, the thing that has the best nucleophilicity is actually iodide, because it's not hindered by these hydrogen bonds as much. It doesn't have a tight shell. It has this big molecular cloud, and some people think it also has kind of a softness. It has this polarizability where that cloud can be pulled towards the carbon and do what it needs to do. So in this case, iodide is a better nucleophile, let me just say, than hydroxide, which is a better nucleophile than fluoride. Now, in an aprotic solution, where all of a sudden the interactions with the solvent are not going to be as significant, then things change. In this situation, basicity matters. So in an aprotic solution, basicity and nucleophilicity correlate. And I'll put an asterisk here, because there's also one other aspect of nucleophilicity that I haven't talked about yet, but I'll talk about it in a second. But in this type of a situation, hydroxide will be better at reacting than fluoride, which will be better at reacting than iodide. And the whole reason why in both situations hydroxide is, I mean, even where it can interact with the solvent, it's still a pretty good nucleophile. Because if you think about hydroxide, and I have to think about this a lot, it has an extra electron, right? If you think about it, you can imagine it's water that took away, let me draw it this way. You can imagine it's water that where a proton left, or where an electron was taken from a proton. So normally you have two pairs, and now you have a third pair right here. This oxygen has 1, 2, 3, 4, 5, 6, 7 valence electrons, one more than neutral oxygen, so it has a negative charge. So it already has an extra an extra electron that gives us negative charge. But oxygen is also more electronegative than hydrogen. So it's also able to get this guy involved a little bit. It's also able to get this guy involved a little bit anyway. So it's a very basic molecule. So even when it might be interfered a little bit by a protic environment like water, it's still a better nucleophile, than something like fluoride. If you take the solvent out of the picture, it's a super strong base, and so it's also going to be a very good nucleophile. Now, the last aspect of nucleophilicity, remember, nucleophilicity is how good something reacts. Now, let's imagine we have something here. So we have two molecules, two hydroxide molecules, right? Two hydroxide molecules. And let's say that this one is, let's just say that this one is just a straight up, this is just a straight up hydroxide. And let's say this one over here has all sorts of things off of it. Let's say it's, it just has this big chain of stuff. It just has this big chain of stuff. I don't know which one. Now, if you were to look at these two molecules, if you were to try to guess which one is going to be a better nucleophile, you should just remember, nucleophilicity is how good something reacts. How good is it getting in there and making a reaction happen? Now, this thing has this big molecule all around it. It might actually make it very hard, if you go back to this circumstance up here, it might make it very hard for it to get in there. We've talked about steric hindrance from the point of view of the carbon, but we haven't really talked about it from the point of view of the nucleophile. In this nucleophile right here, it might be hard for this extra electron right here, for this extra electron right there, to actually get to the target nucleus. It will be hindered. While in this situation, it will be much easier. Even though the group that's reacting, this oxygen that has a negative charge, this extra electron, is on some level fairly equivalent. But this one right here will be much more, it's a much smaller molecule. It'll be less hindered, easier to get in. So this will be a better nucleophile. Better nucleophile. And that's why I wanted to make, I didn't want to make the strong statement that in an aprotic solution, basicity and nucleophilicity are completely correlated, because nucleophilicity still has that other element of, how hindered is it? Is it in an environment where, or is it part of a molecule that will keep it from reacting? Even though it might be a very strong base, if it actually forms a bond, it'll be very strong. So the big thing to remember is that they're just two fundamentally different concepts, and that's why they're two different terms for them. Nucleophilicity, how good is it at reacting, saying nothing about how good the resulting bond is. Basicity is how good is the bond, how badly does it want to react, but it doesn't say how good is it at reacting itself.